Okay, so hybrid 2 was the following, right? So you have it written, I suppose, but it's just good to write it one more time. The lambda is the adversary sends the delta, right? And the challenger samples, the subspace f2 lambda with dimension of a lambda by 2, and then these two vectors ss prime, which are from these canonical strings, right? And samples of B uniformly at random, and an R, and then we defined HB SS prime, ZZ prime was defined to be R XORed with B dot delta if Z prime equals SS prime, right? And HZZ prime. Otherwise, right? And then you output was accept if B sub B equals B sub C equals B, and you reject otherwise, right? Sends back the coset state, right, together with the random string R, sends BC, B and C, you have description of A, you have description of A, okay. You output B sub B, and here you output B sub C. Okay, right, so that was the last one, right, that we were looking at, and they both get access to HBSS prime. Okay, and our objective was to show that this game cannot be won with this game cannot be won with probability more than if you're alive. Okay, so hopefully we'll be able to finish the proof today. So last time we managed to show that, right, and then so last time we managed to show that this output state you can always write in the following form. So phi BC is sum over ij alpha ij for some phi I B tensor psi j c, right? And these phi I, phi B, remember, were, so phi I, so this is recall, this is also recall. So phi, this is like the state right here. So this state is phi BC, right? And the recall was that this phi B, phi I was eigenvectors of pi 0b plus pi 1b by 2, and with eigenvalues, what was it? So for phi it's lambda I, for mu, for psi it's mu I, and these are eigenvectors of pi 0c plus pi 1c by 2. And what was pi 0, pi 1? So these were the, so let's see. So this we had defined to be these projectors, right? So you run, so pi 0b is going to, for example, okay, so this is just to recall, pi 0b would run B on description of A with H0SS prime oracle, okay, and measures this on 0 0 or identity minus 0 0, right? And then runs it backwards, then runs P backwards. Okay, so that was the projector. That's for B, and then you can change it for. So far so good, right? This we did last time, so I'm just quickly trying to recall. I'll close the door. Okay. Okay, and then the statement that we were trying to prove last time was the following. So we were trying to argue that so we were basically going to try to argue about the weights of this state. Okay, and to do that, we'll use the following lemma, which is which says that over the randomness of A S S prime and H S S prime. So this, remember, was saying that H is defined on all points except this S S prime. It's a slightly wonky notation, but okay. Then for every poly P, there exists a negligible function negl such that with overwhelming probability it holds that the sum over the weights is negligible. So lambda I minus half, that is bounded away from half with at least 1 by p. Similarly for j, that it's bounded away from half with at least 1 by p. So the sum of all such weights is going to be negligible. Okay, in N. So that's the statement we were trying to prove. Okay, and lambda I mu j. So this I sort of explained last time as well, that if you have a P of M, you can always write it as the sum of some vectors, right? Sorry, you can write it as in the diagonal basis with some eigenvalues, and if you have some state psi, the probability that you would get the answer corresponding to P and not identity minus P, for example, right? So to get the answer corresponding to P, you can write your psi as, I don't know, some alpha I, right? Because it's an orthonormal basis. So basically, you're checking. So the probability of getting it would just be mod square. So alpha mod square, right? The probability that you get outcome P would just be this object sum over I, right? There's no mod needed because it's already positive. So basically, it's saying, like, what is the probability that this outcome P would appear, and you're changing you're looking at, for different weights, you would have some probability that you'll get outcome corresponding to P. So this is basically doing the same thing. It's just saying that what is the weight being assigned to all the lambda i's, which are either more than half or less than half. So it is collecting all those the weights on all those terms. Makes sense, right? I mean, there's nothing very deep happening. Okay, so let's see how the proof would go. Okay, so let's so actually let's defer the proof and see how to use the statement. Yeah, that's what the paper also does. So let's see how we can use this. Okay, so now it's relatively straightforward. So using this lemma, one has the following. Mm-hmm.
I think when we were discussing the proof idea, like, we used lambda I minus half is greater than negligible, right? Or like even otherwise, this doesn't account for alpha ij's which are negligibly close to half.
The question's not really about alpha ij's, right? The question is really, at least the way these guys are thinking, it seems the question is more about these eigenvalues, because suppose lambda is really small, so for some I lambda is very small, and you have a lot of weight on it, that's okay, right? Because it will not contribute. So I think they're just looking at the weights. They're seeing like, this is the.
So we basically want this summation to be less a negligible function, right? To ensure we don't learn about I and j. Sorry, we don't learn the value.
They'll use it in a specific way. Yes, that will appear eventually. Yes, but at this point,
there could be lambda i's and lambda i's which are negligibly close to half. And there could be exponentially many such lambda i's, because of which the entire summation will become something greater than negligible.
Yeah, but this is a convex sum, right? So you would not really. So there can be as many of these as you want, but you're taking a convex sum over these, so it should not. Yeah, maybe the easiest thing to do is to maybe think of suppose all eigenvalues are 0 or 1, right? Then regardless of how you distribute the weight, if the weight on like even if there are exponentially many terms that have 1, it would only sum to 1. It would never go more than that, because the weight of these is going to be, it's normalized. So you have to be a bit more careful when you're worrying about those exponential sums. This is just a way of distributing the weight, and you're just arguing that the weight on things which are the spectrum here, so things that are away from half, so the weight that you put here is negligible. That's all it's saying. So the rest of the weight has to come from stuff in between. There's nothing very deep happening beyond that. So yeah, you could have exponentially many terms, but the thing has to be normalized, so it's okay. I don't know if it answers your question, but
I think it would be I don't see where we're using it. So maybe once we see.
Yeah. I mean, the statement should be clear. How we use it will become clear in just a moment. Okay. I mean, there is some problem with it, but that is not, at least that's not what I thought was the problem. So we'll see if there's an error in the paper. Okay, so the claim is now the following. So the claim is the state phi bc produced by A for every polynomial P is negligibly close to the following state. So basically phi bc is negligibly close. So I'm just using this notation. It means that you take the difference in the norm and it would be negligible. Lambda I minus half at most 1 by p alpha ij phi I psi j plus, maybe let me write it in the next line, it's better. So plus sum over I such that lambda I minus half is greater than 1 by p, and j such that mu j minus half is at most 1 by p. Okay. Alpha ij phi I p tensor psi j c. Oh shoot, I have to silence my phone. Okay, so that's the statement. Okay, and we're going to write this whole thing, so just the bottom thing as define it to be phi prime sub c. Okay, and this thing we're going to define to be phi prime sub b. Okay. Okay, so now what's the intuition? Why are we doing this? Because the story is the following, that phi prime b captures that A cannot win. Oh, sorry, that B cannot win. Wait. So lambda I was for phi I, is it? Yes. Okay, so lambda is for phi I, right? And here the success probability is, so I had drawn this, right? So this was half, right? And then this is like the 1 by p interval. This is half minus 1. Oh, sorry. Let's say lambda, or let's say eigenvalue. So let's say val minus half is at most 1 by p, right, for some p. So this term is saying that for alpha, for b, this is the projector, right? That basically corresponds to guessing it correctly, right? And the game was also, right, that with half probability, the challenger gives you with half probability, it gives you h0, with half probability, it gives you h1. So essentially the success probability would just be this object, right, that you make the measurement. And then, and as per this definition, you're also checking that it's the correct thing, right? Like, so if it was 1 here, like you can put a b if you want, little b, right? So you're checking that you're actually giving the correct answer as well. Okay, so the projectors actually correspond to the winning probability for that. This is clear, right? That the projector corresponds to the winning probability. Okay, and then this expression is saying what? It's just saying that the eigenvalues of that observable, basically following essentially this line of reasoning. The eigenvalue of the projector, so all the weight that this state is assigning to the eigenvalues of the projector which are within this, I need to rephrase my sentence, but so this state is basically assigning, at least in the first part, all the weight in this interval, right, for the eigenvalues. And this is true for all 1 by p, right? So it's essentially, in a very narrow interval, so it's essentially just outputting with probability half, because the statement is for all polys, right? So you can do this for all polys and it will just keep shrinking. Okay, so it's essentially negligible. So you're basically just negligibly around half. So your winning probability is essentially just half for this first term, for Bob. Okay, and you can run the same argument for Charlie, and you'll get the analogous statement, but with mu's instead of lambdas. Okay, because the mu's are bounded by 1 by p. Here lambdas were bounded by 1 by p. Okay. So assuming this claim is correct, you know that either Alice is going to lose or Bob is going to lose. So in this term, either Bob is going to lose or Charlie is going to lose. So the first term Bob is going to lose, the second term Charlie is going to lose. Okay, that's why they are called these phi b, phi c. So that's the intuition. So phi prime c captures that. Right? And this essentially tells you that you cannot win this game, right? Because they cannot simultaneously output it. So one party is always going to lose, regardless of which term you use.
Why first term is independent of mu? Like second term you have extra condition that mu j minus half is.
Yeah, I think they may have left it. Like I think you can put it. You can say 1 by p. It's probably okay. It's not. Or even if you don't, actually, I think it's okay. It doesn't really matter. But okay. Because your main point is that one of them is losing. It's okay if both of them lose. So that's not really an issue. Okay. So that's the story. So now.
Also, there should be a third term where both are less than equal to 1 by.
Yeah, that's why I don't think they added this term. Because if you don't add it, then both less is also absorbed in this, right?
Yes, greater and less both.
Yeah, that's. But it doesn't change much. Okay, good. Okay, so let's prove the claim. So okay, at this point it should be clear that proving the claim completes what we want to show, right? Okay, good. So let's try to prove the claim.
Still have the same problem.
Mm-hmm.
Here, we can have 1 by poly advantage for winning for both parties simultaneously.
You can have 1 by poly advantage for both parties winning simultaneously. Yeah, but this is true. The statement is true for every poly. So
So there exists a poly for which you can win with 1 by 2, 1 by 2, sorry, 1 by 2 plus poly, like half plus poly advantage for both adversaries.
yeah, but the bound is true for all polys. So basically it's this statement, right? So if I don't know, if f is less than 1 by p for all p, then f is negligible.
Right.
Yeah.
So for all polys, I can win with half plus poly advantage. Right.
I can win with at most half plus poly
Yeah,
advantage.
but for both adversaries.
Yeah.
Which means both the adversaries can win with half plus poly advantage.
But
At
that-
most for all poly. Like, so the statement is like you're giving better and better bounds, right? You're saying that, so this statement is saying that you can win with at most 1 by p for some p, and you can make the p bigger, so 1 by p0, p1. You can take a family of polynomials, right? So your bound will keep shrinking, and eventually you're left with the fact that you can win with negligible. The statement is not that you can win with 1 by p, it's like that you can win with at most 1 by p, and you're refining the statement. Like the statement holds for all poly. So if you're thinking you can win with this probability, that's not true. Because not only is the bound true for this poly, it's also true for that poly, and so on.
So they're saying there exists.
They're saying for every poly there is a negligible function. So this is negligibly close. So you can, so more formally for every poly you can show that you'll be negligibly close to something that wins with 1 by p around it. But the polynomial, you can keep taking a bigger polynomial, and you would still be negligibly close. You can always approximate it. That's what it's saying. So in the end you would be like in this little interval, and that's essentially negligible. That's the statement here. Yeah. Yeah, it's basically just this, right? Like, so instead of trying to do negligible directly, they're doing it for all poly. Does that make sense? Okay, very good. So now let's move on to the.
So does this claim follow from lemma 4.1? That
Yeah, that's what we'll prove now. Yeah, exactly. Yeah, basically you just write out the success probability in terms of the projectors, you open it up, and then some of the terms will be negligible, essentially, from the lemma. Right, because the lemma is saying all terms that are greater than 1 by p would vanish. So when you write it out, you'll see that cross terms disappear.
All the terms greater than 1 by p would vanish, but there would still be terms with 1 by p which won't vanish. Right?
no, it's other way around.
It's strictly, yeah.
So you could have lambda I is half plus 1 by p, and mu j also is half plus 1 by p.
Yeah. You could, but that's true for every, like you're saying that you can approximate. So like the approximation would be different, right? It's saying that you can negligibly approximate it for any p.
So I'm not understanding his question. So what is
I think his concern, at least the way I understand it, is that he's saying that look, if I can show that there exists one state for which you win with advantage 1 by p, then
Both parties.
yeah, both parties win with advantage.
That statement says it is not possible, right? Because you are saying that the state will not contain terms like this.
No, but like if you see the second term,
Yes.
I is such that lambda I minus half is greater than 1 by p, and j can be such that mu j minus half is equal to 1 by p, right?
Yeah.
So which means mu j is half plus 1 by p, and lambda I is greater than half plus 1 by p.
But like Atul said, that p is any p, right? So that would
Yeah,
just
so-
be
So I suppose the somehow the resolution would probably come from the fact that the the weight distribution has to be such that eventually you will not have. So even if you do have one, so if you have support on some eigenvalue which is equal to say 1 by p, the weight on that thing cannot be very big, because somehow this statement holds for all p's. So not only is this valid for some specific p, it's also valid for some other p, right? So it couldn't be that that you have like so half plus 1 by p.
I think I would have been fine if it was just strictly lesser than instead of lesser than equal to.
In that case, it excludes the half plus 1 by p, right?
That is what we want.
Not really. I mean, that's just a continue. Like you can be arbitrarily close to it. That really won't change anything, right? Like if your concern is legitimately about that somehow the expression says I can win with this probability, exactly this probability, then if you make it strictly less, it will be very close to this, like arbitrarily close. It really doesn't make. But your argument would still be, your question should still exist. And I think the way to answer your question is that it is true that you will win with half plus 1 by p probability, but with some weight, right? There will be some weight associated with it. So overall, the winning probability would be some average, right, over all of these things. But also the same statement, the same characterization also holds for some other poly, right, which would be 1 by p2, say, for example, right? So you're getting different characterizations and they're all the same. So it must be the case that even if you do win with some high probability, the weight somehow add up so that because I'm not saying anything specifically about what the weight of alpha ij is in that sense. So yeah. Okay. So hopefully that clarifies the 1 by p thing. Yeah, but maybe there's something more to it. I mean, you can think about it if it's not convincing. At least to me it seems okay, but maybe there's something more. Yeah. All right. So then now, yeah, and I use this psi negligible rate phi to mean psi minus phi is negligible. Okay. This is just in case it wasn't obvious. Okay. So now, so this I kind of said in words already. So let me just write it down. So one can write the probability that ABC win as at most half pi 0p tensor pi 0c acting on phi bc plus half pi 1b tensor pi 1c on phi bc, right? So this I already argued a second ago, right? This is this okay? The winning probability. Okay, and this is, so this corresponds to HSS prime program to, corresponding to, what did we do? We programmed it to little r, and this one corresponds to programming to r plus delta, right? Depending on whether s was 0 or not, right? Is this okay? This is just this statement. So when b is 0, you program it to r, otherwise you program it to r plus delta, right? So that's all by definition of pi. Okay. So let's make some more progress. Should I remove these definitions? Will we remember them, or should I write here? Maybe let's just write here. I think it's fine. This is just a bunch of calculation now. I should say one thing. We'll complete the, we'll prove the claim in just a second. It's basically the proof of this lemma that actually uses, that shows how you extract the S's that were there in the previous game. So the extraction actually happens in this step. Once you know this step, then it's just algebra. So it's relatively straightforward. Okay, so let's do this. So now it's just calculation, like I said. How do you spell calculation? What the hell? Okay, so this is some simple calculation. So what we're going to do is we're going to substitute 5bc with 5 prime b and 5 prime c. Okay, which we can like up to negligible error. Okay, so this is going to be half pi 0b tensor pi 0c acting on 5 prime b plus 5 prime c, okay, mod square plus half of pi 0c tensor pi 1b and pi 1c 5 prime b plus 5 prime c.
So you were using previous claim, right?
I am using the.
So you wrote 5bc negligibly close to 5 prime c plus 5 prime b.
I am not. Am I doing the proof of the claim? I'm not doing the proof of the claim yet.
No, I'm just
So-
asking that you are using the claim.
Yeah, I was trying to see if I'm proving the claim or using the claims. I'm just checking. Give me a second if I'm. Yeah. Okay. So the claim was almost immediate from the lemma, I guess, right? Because you're removing all of these terms. So the claim essentially is like straightforward from the lemma, right? So I think they just skipped the proof because it was elementary. And now we're using the claim to show that you will win with utmost negligible, which I hand-wavily argued earlier. So we're now actually doing it properly. Okay. So assuming the claim, we'll show that the winning probability in this game is going to be at most half plus negligible. And to do that, we're using the claim. Exactly.
There could be one more trivial step in between where the states were closed and you are assuming that this mod square will also be closed.
Yeah. This is just the probability that you get a certain. So basically, if they're close, if the states are close, then they'll be close in trace distance, which also means there'll be like no operation should be able to distinguish them, right? So it should follow. Yeah.
The states are closed, then any measurement.
Yeah. Okay. Okay, so therefore we're just going to apply the same measurement, except instead of the original state, we'll apply it to the characterization we got from the claim, and now we'll just do the calculation and see what we get. I have a feeling we'll be able to finish everything today, so that's very good. So 5 prime b, pi b0 tensor pi c0 5 prime b plus 5 prime b pi 1b tensor pi 1c 5 prime b. It's so nice to have some calculation eventually.
It's trivial, right? I'm not missing something when I'm replacing it.
Just a second. Let me write down the expression, then I'll come back. At the moment here, what I'm doing is very straightforward. There's nothing very deep happening here. And then the real part, 5 prime b, pi 0b, tensor pi c0, 5 prime c. Oh, do you want to do it on the projector? Ah, fine, I'll do it. It's okay.
I'm just asking that.
5 prime c. Yeah, I just expanded it, didn't do anything there's nothing non-trivial happening here. Okay, and this okay, so this is the non-trivial step, quote unquote. Okay, so it's the same expression except we are going to replace pi 0 c with identity, right? So this only increases possibly, right, the value, because you're adding a POVM element. Then identity tensor pi 0 c plus identity tensor pi 1 c, and plus the real part is the same. Okay, so all I did was I replaced this pi 0 c with identity, and I replaced some of the operators with identity. Okay, and the reason to do that is because the characterization was in terms of, like, here there's phi b, and I know the characterization in terms of pi 0 b acting on phi b, right? So this thing, if you make it identity, it makes our life easier.
But this is marker in the, at least where you have phi prime b, phi prime c.
Yeah, there you have to argue what happens there. Exactly.
But you replace everywhere by identity.
No. The ditto marks are basically saying that it's exactly the same expression as before. The expressions that have changed, I've written them down. So, for example, in the real part, this part is the same. I have not changed it. This is the one where you have cross terms,
Okay,
right?
yeah, okay.
Yeah. Oh, I forgot a p. Okay. And now. Okay. The story is we bound each term separately. Okay, so the first one is half phi prime b, pi 0 b tensor identity, phi prime b plus phi prime b pi 1b tensor identity, phi prime b, right? This is this guy. So you can add the pi 0 pi 1, right, and this will give you a very nice form, right, for which we have the characterization. Tensor identity, right? Is this okay? And then what will this be? From what we know. So you look at the definition of phi prime b. What bound do you guys think we can use? So what is the highest eigenvalue it can get? 5 prime b.
Half less individual.
Yeah. So you get half plus 1 by p, since we are looking at one specific p, right? And then whatever weight, whatever the normalization of phi prime b is, right? Because these are not normalized since we wrote them into two parts. But this is at most 1 anyway, so that's what you. Right? Is that okay? And so it's similarly for the C part, right? So you'll have identity tensor pi c on 1, phi prime c. And this would be what? This would also be half plus 1 by p, for exactly the same reason, right? Phi prime c 1 square. Right?
Wouldn't the two projectors add up to identity?
Oh no, this is a question that Uttam asked a while ago. So what's the answer? Why don't they add up to identity? Because it's misleadingly labeled. The projectors are running different things, right? So this is running H. Yeah. Oh shoot. Yeah, it's running H sub p, right? So they're not identity. Yeah, that's a good question. Okay. All good? Okay, very well. Yeah, sorry, there's a lot of moving pieces, right? So it's a bit hard to keep track of everything. Okay, and the third part is, yeah, so the third part is actually interesting. So let's do the third part. So I'm going to erase this right hand side of the board because we already know this. The third part is going to show that this part is going to disappear, and we'll use Jordan's lemma, like the corollary that we had the other day. We're going to use that. So let's quickly recall what the statement was. So this is informal recall, okay? You should look at the formal statement to be correct, fully correct. So for pi 0, pi 1 projectors, right, if phi 0, phi 1 are eigenvectors with eigenvalues lambda 0, are projectors for omega pi 0 plus 1 minus omega pi 1 with eigenvalue lambda 0, lambda 1. Okay, if that's the setup, then we argued last time that phi 0 acting on pi 0, phi 1 is the same as phi 0 acting on pi 1, phi 1, and this is 0 when lambda 0 and lambda 1 are distinct, and lambda 0 plus lambda 1 does not add up to 1. Okay, so now we're going to use that fact. So let's keep it in mind. So NB3 says the following. It says that the real part of phi prime p, pi 0 b tensor pi 0 c, phi prime c is 0. Okay, and so to do this we basically expand phi prime p and phi prime c. Okay, so this would give you what? So this part we're going to write as follows. So we'll write it as sum over. Oh, today there's a lot of writing. Lambda I minus half 1 by p, and then sum over I prime lambda I prime minus half greater than 1 by p, and j prime mu j prime minus half at most 1 by p, right? And then alpha dagger ij, alpha I prime j prime, phi I, pi 0 b, phi I prime, psi I, pi 0 c, psi j prime. Okay, and so I didn't do anything. I just expanded it, right, and put the constraints on the summation. And now note that all possible I prime satisfy lambda I plus lambda I prime not equal to 1, right? And so this tells us, using the corollary, that phi I pi 0 b, phi I prime is 0. Is that okay? So it's a very cool application of this Jordan's lemmas, the characterization and the corollary they had. This was some corollary 2 point something, I forget. 2.4. Okay, so this part turns out to be orthogonal, and so they disappear, and then this part is you can bound it in terms of 1 plus 1 by p. Oh, I erased it. Okay.
So why this is not equal to 1 lambda I plus lambda I prime?
Well, because these are the bounds, right? The indices are like, something is like in this interval and something is outside, and so then you can see they'll never add up to 1.
But 1 is less than equal to, right?
Mm-hmm.
So you have less than equal to and greater than equal to same number, then there seems a place where they might add up to 1.
Yeah, so okay, let's see. I had sorted it out for myself. Okay, so you're saying for all I and I prime, it is the case that, yeah, so I think the point is that it has, this one is strictly greater than 1 by p, right? Like, I think you have to have them be like equality on both sides. If one of them is strict, then you can never get exactly 1.
I think that is good enough.
Like basically you have to match like exactly at the boundary, right, to add up to the thing. So one of them will always be strictly less, so you won't be able to add it. Okay, so and then one can repeat a similar. So we did it for this term, right? You can also do it for that term. Essentially the same argument. Okay, and then so now the story. So you combine to get that, you know, the final bound would be half plus 1 by p plus negligible for all poly. Okay, which basically means it's at most half plus negligible. Okay, so this is the first time we've proved that. So yeah, that this thing cannot actually work. We did make a lot of very strong assumptions. Yeah, wow, we might actually be able to finish the proof. I'm so glad. Nice. Okay, this part is fine. Okay, so now it remains to prove this lemma, right? This is the main thing that we need to establish. So let's do that. So we don't need the game anymore, do we? No, we will need the game. It's going to extract things. Okay. Let's remove this part. So next time we'll do pseudo-randomness and things like this from Andrea's lectures. So he gave these lectures at Oxford, I think, at some point, and he was kind enough to share his lecture notes. So let's see how it goes. Let's hope we finish it this time. Okay. So clearly it remains to establish lemma 4.12 or 4.12 if you want to be strict about it. So let's do the proof. So proof of lemma 4.12. So here are some recalls, which I suppose we have already written. No. Okay, so we recall that phi BC has that form. Did I remove it? Oh yeah, there's the same recall. Okay, so recall the form of phi BC. Okay. Yeah, no, I don't think we need the recall here. Actually, we have it all on the board already. Good. Okay, and now we suppose. Okay, so story proof is by construction or by contradiction, by construction. How does it work? Okay, so the strategy, that was the strategy. Now we suppose that, oh sorry, that wasn't story, that was strategy. Yeah. Not that it matters, but. Okay, so suppose there exists an adversary ABC, okay, such that W, the weight being bounded, okay, such that W, the weight being bounded, I am not fully sure what that means, let's see, is non-negligible. So W is greater than 1 by Q lambda. So I guess the weight being bounded must mean the success probability rate that with which they're going to win. Okay, so for some poly Q with non-negligible probability eta lambda, The weight on what? Okay, I guess it'll become a little more clear. I think I've forgotten what they were talking about here. That is annoying. Oh, okay. That's because I skipped the recall. Sorry. Okay, so the weight is this. Forgive me. This is what they're calling the weight. Okay. Otherwise, it wasn't making sense. Sorry. Okay. So this is what they're calling W, the weight, and the statement here says that with overwhelming probability, it holds that this W is going to be at most negligible. So the contradiction would be that there exists some non-negligible function, right, for which W is at most 1 by poly. Okay. So actually, they could have said 1 by non-negligible here, but it's probably the same. So it's okay.
Beta lambda tells you that this adversary exists.
Oh. What? Beta lambda?
Eta lambda. So there was Q lambda that is telling
Yeah. The eta lambda is the probability. So there will be a distribution on the weights W apparently. The distribution is coming over these randomness. So depending on the choice of the different oracles and so on, you will have some distribution over different W's, right? Because once you fix them, you can compute W.
Yeah.
So there will be some distribution over W, and they're saying that over this randomness with some non-negligible probability, you will have some W which is non-negligible. Okay, so that's the contrapositive. Okay, and good. And the story is the following. So given such an ABC, we construct the following. Construct the following adversary. Following adversary A prime, B prime, C prime. Okay, that breaks the regular MOE game. In definition 4.5. Okay, so this was essentially the search version, right, where you give access to the oracles, and you're not supposed to just distinguish. You're actually supposed to output the entire string. Okay, without the random oracles, right? There was no random oracles, but you had access to the membership oracles, right? And this is, remember, why we wanted to use coset states instead of Wiesner states. So now we're going to use that. So we're going to start with this adversary and construct an adversary that breaks that game, and that game we will not prove it, but that game we know from previous works that you cannot win that game with probability more than half. Okay, so that was so that would mean that such an adversary cannot exist, because we'll construct one that will extract with high probability, but that will be a contradiction. Okay, good. Okay, so it's going to break this game. Okay, and what that means is that it will have it makes both B prime and C prime output SS prime with non-negligible probability, right? SS prime with the coset, the input, right? The vectors that were hidden. Okay, good. So what is the construction? So let's look at the construction now. I'll write the construction on the right, so we have some space. So the construction is as follows. So number one is A prime, B prime, C prime. Get oracle access P A plus S and P A perp plus S prime. Right? So that's fine. So now, what does the construction do? The construction is as follows. ASS prime This is A prime. This is A. Okay, so A prime is going to get the coset state as an input, right? And not make it too restricted. And A is going to, they can access A, right? So they'll run A. A is going to output some delta, and A prime is going to sample a random R and sample a random oracle itself, right? Because remember, the original game has no random oracle, right? It was just an information theoretic statement. And then it uses H as SS prime, okay? So recall this was makes H at SS prime output U independently, right? Remember from the hybrid one, I think it was, we have this, right? So at SS prime, it basically just outputs a random U. Okay, and now whenever A has to access the random oracle, okay, A prime is going to simulate it for them because it chose the random oracle. Okay. So far so good. I've not done anything. And then A is going to output B and C. Okay. And A prime is going to forward B and C as it is to B prime and C prime. And B prime and C prime are going to be defined in just a second, but they're going to output SP, SP prime and SC, SC prime. Okay, and what are B prime and C prime? Oh no, I forgot to tell you something. Okay, so we're going to assume another lemma, which I'll not prove. Okay, so I think we'll stop there. I'll give it to you as reading. But let's look at the construction. Okay, so now we can remove this part. I think it's fine. Okay, so now we have to specify these B primes and C primes. So for this, we are going to recall the definitions of pi 0b and pi 1b. Right, so we actually have them written here, which is good. Okay. Yeah, and just a quick reminder, this was, H0 SS prime with R, and this can be seen as H1 SS prime equals R plus delta. So yeah, this is same as H0 SS prime, except these are the differences. Similarly, same as H1 SS prime, except okay. Right, so H0 H1 yeah, maybe actually I should state same as HSS prime, except that it satisfies. Yeah, okay, good. Okay, so that's the only difference. Okay, so this uses H0 SS prime, and this uses H1 SS prime. Okay, So that was the difference, and then we know what the definitions are. Good. And okay, so with this, what we can and remember we argued that you can do this efficiently, right? We said that you can use the membership oracle to query and make sure that it's sorry, you can check whether the query is actually on SS prime and so on without actually knowing SS prime. Okay, so B prime then proceeds as follows. Okay, so first it's going to apply. Oh, I didn't tell you this. Okay, so it applies the efficient threshold measurement. I don't know why it's called SATI or whatever, but these are the measurements. I'll tell you what the statement is in just a second, okay? So in theorem 2.8, okay, with projectors where P is pi 0b plus pi 1b and Q is identity minus P. Gamma is some value 3 by 4p, epsilon is 1 by 4p. We will not worry too much about the parameters at the moment. Delta is 2 to the minus lambda. Okay. So I haven't told you what these projectors are, okay, at the moment, but so we'll define it in just a moment. But these projectors are specified by, you have to give them two projectors, P and Q, okay. You have to give it some gamma, and this will give you like a measurement. So it will give you a procedure that basically corresponds to a measurement, okay. And then if the outcome of this procedure is 1, outcome is 1, okay, then B prime runs B on the leftover state, okay, with H0 or H1 picked at random. You remember we had the identical challenge mode and the independent challenge mode, so this is sort of where it's used, okay. So this part is still mysterious, I haven't told you what this is, but condition on the outcome that this procedure gives you 1, B prime is going to run B on whatever the leftover state is, and it will, because you know B prime doesn't know, right, it doesn't know whether H0 was used or H1 was used, it has no idea, so it will just randomly pick one of them and produce the answer. And B prime, oh sorry, it doesn't produce the answer, it just runs it, okay, and then B prime is going to measure and output a random query. B makes to the random oracle. Okay, so it's going to run it, and then at some point, at some random time, it will just measure the query register and output what was being queried. Okay, and this output is what is going to be SS prime. Okay, so this is 3, and then 4 is, you know, C prime is similarly defined. Okay, so before we do the analysis, I have to tell you what this measurement is, right? Because otherwise things won't make as much sense. Let's do that. Yeah, sorry, I skipped a bunch of prerequisites because if you just do like a list of prerequisites, then it becomes too much. Oh my god, you're dying. Okay.
What happens when the outcome is not 1?
I think then it just fails. So they'll argue that the outcome will be 1 with non-negligible probability. Yeah, that's a good point. Yeah, thanks. Oh, what the hell? Let's do it. Okay. So what part should I remove? I think we can remove that part probably now, right? Yeah, which do you guys think should I remove among 1, 2, 3, 4?
The second
You can
portion.
remove the adversary and
Yeah, that's a good idea. We'll try. And also remove.
You can remove this second part because
We need more space. It's okay. I think I'll just.
the statement of lemma 4.1.
Yeah, this you don't need. It's okay. I think I'll write down when we need to. I think it's just not possible. It's fine. Yeah, for these big proofs, I think it's good to have. I don't know what the solution is here. Okay. So theorem 2.5. Yeah, maybe I should have started with the story for this part. Oh no, this is long. Yeah, I'm just trying to decide what is, because I should have prepared to have simplified this. Okay, let me actually just state the lemma directly, and then let's see the theorem, and let's see if we are okay with it. If you're okay with it, then we can maybe continue with the proof, and we don't have to do too much of the intuition building. Okay, so let's just state the theorem. So which one is it using? 2.8, right? Yeah. Okay. Let's prove theorem. So here's the statement. So 2.8 says the following. So it's called efficient symmetric threshold measurement. This is also one of those magical steps that I have not proved myself. It's from a paper of Zandri's. And so this is what it says. I'll give you like the asymmetric version first. I think it will make a bit more sense. Let me give you the asymmetric version first, okay? Okay, so what is the statement? The statement is let P sub B be P sub B, P sub Q. Okay, and these are binary outcome POVM. Binary outcome POVM acting on H sub B. Okay, that are a mixture of projectors. For all B in 1, 2. Okay, so basically you have Hilbert space H1, H2, and you know, this P1 acts on H1, right? P2 acts on H2, and this thing is just P1 Q1, and this is P2 Q2, right? And they're assuming that these POVM elements are they're basically just a mixture of projectors. Okay, so that's the premise. Okay, and then they write it explicitly as follows. So they say that in some basis, right, they are positive operators, so we can diagonalize them like we did earlier, right? So you can do that, and then you pick gamma 1, gamma 2 in 0, 1. and you have epsilon b between. So this part is not all that relevant, like the details are not super relevant in the sense that conceptually they're not very important at the moment. Okay, and this delta greater than 0 is arbitrarily chosen. Okay. So then there exist efficient measurements, efficient binary outcome algorithms. Okay. Oh my God, algorithms. Okay. Interpreted as POVM element with outcome 1, which is what this was, right? We were saying outcome 1, right? Where was it? If the outcome is 1, that's what it basically meant, that it's describing some measurement which is efficient, and when it succeeds it will output 1 basically. Okay. And so what is this procedure? It's ATI. I think S is probably symmetric. T is threshold. A and I have no idea. Okay. Such that for all rho in density matrix on H1, tensor density matrix on H2, the following about the product, algorithm, product algorithm holds. Product algorithm meaning you run ATI epsilon delta on P1 gamma 1. Okay, tensor you run it on ATI epsilon delta on P2 gamma 2. Even I can't read it at this point, but okay. So what are the statements? Okay, so first of all, the premise should be clear, right? So you have these POVM for both. Using this, so they're looking at I'm actually a bit confused on the one. This P sub B is, yeah, they're not worried about Q sub B. So you're given, you're given this binary outcome POVM. You expand it in this diagonal basis, and given the description of these POVMs, these curly P's, and these other parameters, you can construct an efficient program, okay, which will satisfy the following. Okay, so you're acting on Hilbert space 1, tensored with acting on Hilbert space 2 with these efficient algorithms, and they satisfy the following properties. So we're going to, okay, so the first property is that you let E greater than gamma P and E at most gamma and E strictly less than gamma. So these are threshold measurements. So this basically are projectors on, these are projectors on eigenvalues. These eigenvalues at most gamma, right? And this one is at least. So that's all. Because these are just projectors on these things. So you can write them explicitly if you want. Okay. So that's fine. Okay. and then the probability of measuring 1 on both registers. So here, okay, so you run this projective measurement, so probability of measuring 1 on both registers satisfies the following. So trace ATI P1 gamma 1 epsilon delta tensor this measurement P2 gamma 2 epsilon delta on row. Okay, so if you know that, so you make this measurement, okay, and the probability that it will output 1 on both, right, which we are writing like this, is going to be what? It's going to be exactly the following, that you made this projective measurement, projective measurement, I'm saying this threshold measurement on the same state, okay, but you're just projecting on the eigenvalues being greater than a certain value, okay, minus 2 delta. 2 delta is your error. Okay, so that's the second statement. And so far, of course, you could have just put identity here, right? So identity will always output 1, so it's nothing meaningful yet, right? So you can always trivially satisfy the thing. To make it meaningful, you have the second statement, which says the post measurement state because remember POVM elements don't specify the post measurement state, right? So that's why there's like some algorithm which is doing the measurement. Okay, so the post measurement state rho prime after getting 1 1, okay, so in this procedure is 4 delta close to a state in span of psi 1I psi 2j ij are such that the eigenvalues are greater than the corresponding this gamma 1 gamma 2 except for this penalty by epsilon. Okay, so somehow you have a procedure, right, that will output 2 1s with the same probability as if you had applied the projector, okay, on those eigenvalues, and it will be such that the post measurement state would in fact be spanned by vectors that in fact have individually eigenvalues greater than what you were projecting on in the beginning. Okay, and of course you can do it trivially, right? If I give you the POVM, you can write out the POVM. The crucial part is you can do it efficiently. Okay, so that's the non-trivial thing. And finally, there's like a question about the runtime. So the runtime is runtime of the algorithm is poly-in. Runtime of P1, P2, 1 by epsilon log 1 by delta. I'm just writing the full statement because it's good to have the full statement since I have it written. But so it's obviously if your measurements themselves are inefficient, then obviously you don't expect anything. But assuming the measurement itself is efficient, so the runtime is going to be polynomial in the runtime of the measurements, and 1 by epsilon and log 1 by delta. Okay, so that was this magical step. So the difference is here I said, these are efficient threshold measurements. When you make them symmetric, instead of saying it's greater than gamma or less than gamma, you'll like do the half plus whatever value you want. So you'll say lambda plus lambda minus half is at most gamma, or at basically it's the same idea except that you're doing it symmetric. But it becomes a bit more ugly to explain. So I think this is easier. Okay, but the idea is the same, that once you run the measurement and you get ones on both, okay, then the post measurement state would be spanned by this, like you have a characterization for the post measurement state. And the probability of you getting ones on both is the same as that if you had applied the projector. Okay, so yeah, maybe actually I think maybe it's good to pause here, because do we want to try? Let's try. Let's see if we can make it. Okay. Okay, so I'll erase this. This much is like all that we need to know is that it can be applied efficiently, and it will project on the space with eigenvectors which are at least the eigenvalues are at least as high for both cases. Okay. We're almost done. There's just like one page worth of argument left, and then we're done. Okay, so now, where's the chunk? So, okay. So given A prime, B prime, C prime, we argue that W, which was the weight, right, on the weight that both of them were at most P and at most Q, right?
Greater than P.
Oh, they were both greater than P. Okay, so that weight is going to be at least it's going to be non-negligible. Sorry, no. If that weight is non-negligible, it would imply that A prime, B prime, C prime extracts SS prime. Okay, so from theorem 2.8, right, which we just erased, from the first point and conditioned on the event conditioned on W is greater than 1 by Q, okay, which recall happens with probability eta, right, which was non-negligible. It follows that both B prime and C prime get outcome 1 with probability 1 by Q minus 2 delta, right? Because because the condition on the eigenvalues was itself that it has to be greater than P and Q, right? And the weight on that state was 1 by Q, right? So if you look at and that's exactly what point 1 was, right? Point 1 was saying that both projectors are satisfied. So the probability with which that would happen is we know that it would be this value, just from the premise, right, of for contradiction. Okay, good. And then, okay, no, I think I'll stop because, yeah, okay, let me just write one last statement, then we go. Okay, so and if both outcomes are 1, okay, then the leftover state is 4 delta close to this state. Okay. Right, because it has to be in the span of these guys, right, that are at least as high. Okay, and then we'll use this characterization to further argue that we'll be able to extract it. Okay, so this is probably a good time to stop. So we understood that there's this nice measurement which happens to be efficient that can be applied, and when the outcome is 1 1, we get a nice characterization on what states it could be, like the post measurement state, where in what subspace it lies, and then from this we'll be able to argue that you can extract. Okay, thank you. Almost there.